the chapter today is to get you to understand two vocabulary words. One of the vocabulary words is discrete, and one is continuous. So, discrete variables are numbers that are countable. So it's something that has a distinct set countable value. The numbers such as typically whole numbers, 0, 1, 2, 3, 4, and they would be related to something like this. Say the number of children in a family. Okay, so that's a variable, that's an unknown, but from family to family, that's going to be a discrete, countable amount. All right, so that's an example of discrete. Continuous is the other one. Continuous is going to be infinite possibilities, infinitely small. So, if we had something, that had decimal values, that could be infinitesimally small, such as you could measure your height with very, very, very small decimal values, and so on. You could measure the, grams of sugar in an orange, in infinitesimally small decimals, okay? Small amounts. So, here's some examples. Let's run through these really quickly. Are these an example of discrete or continuous? Number of desks in a classroom. Good. So that's a distinct set amount, countable. The fuel efficiency of an automobile. Continuous. The distance that a person throws a baseball. Okay, so that's a measurement, and typically measurements I could measure in little small, infinitesimal, super small decimals. So that would be continuous. But the number of questions on a statistics exam, that's going to be a set countable amount, so that's discrete. All right. Now, that was goal number 1. Okay, done with that. Goal number 2 is to learn how to compute this thing called an expected value, also referred to as the mean. The mean and the expected value are the same thing. Okay? And I'm going to teach you how to read and understand this formula. This formula will not be, you don't have to memorize it. It's on the formula chart, so I'm giving it to you from now on. Now, in years past, when I have had multiple days to get all this information, we actually physically played this game. We do not have time to play this game, so we're going to talk through it, and you're just going to have to imagine it. So, here we go. We're going to pretend like you all brought $5 with you today. Okay, you all brought your own $5. And so here's how you play this game. You can buy a stamp, with whatever profit you have left over. So that's what that would have been, what was at stake for you. All right, so here we go. Yes. So, here's how this works. You have to pay me $5 to play the game. And what you will do for the game is you will draw from a deck of cards. No jokers. Okay. If you draw an ace of hearts, I will give you $100. So, how that works is you pay me $5 to play. If you draw the ace of hearts, what's the probability of you drawing the ace of hearts? 1 out of 52. That's the probability of that happening. Then, I'll give you $100 back. What did you actually profit? You got 95 bucks. If you paid me $5 first, I gave you 100. Okay. Good? Yep. Lady Anderson, who didn't need it, of all people. Yes. Yes. Okay, next, the other option for...
Isn't that illegal in the state?
Yeah, right. So that's why you do this. Okay, so for any other ace, if you get any other ace, what's the probability of that? Any other ace?
4 out of 52.
No, not 4 out of 52. Any other ace. So there's 3 other aces because, the ace of hearts is the big winner. So any other ace, it's 3 out of 52, and you pay me $5 to play, and you pick a card. If you pick any other ace, I give you $10 back. So what have you actually profited? Okay. All right. Now, for any other heart than the one big bonus heart, that was the ace. So how many other hearts is that? That's the 12 out of 52. So, for any other heart, you pay me $5, you pick a card, you get any other heart, I'm going to give you your $5 back. So in essence, you did what? You broke even.
This was a game in Vegas.
You would broke even. Now, if you draw any other card,
You're done.
what's the probability of drawing another card? How many other cards is there? Well, there's 16 that are winners.
36.
So there are 36 that are not winners.
Who's good at math?
Okay. So yes, I would not have gone over these odds with you before we played the game. But since we're going through this right now and we're not actually getting to play the game, so because I guarantee you the casino is the one who would be winning out. And in this case, I'm the one who's the owner of the game. I would be winning out. I would be making a profit. And overall, you guys would be losing. So let's talk about that. We're going to create this thing called a probability model to show the probability of each event. So my first question is this a discrete or continuous amount of happenings, amount of events? It is discrete. There are 4 possible events. Okay? So that is a countable amount of events that can happen. So, on the next page, you have this chart here. And we're actually not going to call this payoffs. We're going to call this profit for Miss McClellan. Because, you know, man, my son, he wants, is it Dr. Beats or just Beats? What do you call it? Dre Beats? Dre Beats, not Dr. Beats? I don't know. It tells you, see, I'm away.
Wait, how old is your son?
I don't know. He's 11.
And you're buying him.
And he wants Beats. That's what he wants for his Christmas and birthday.
When I was 11, I was working for college.
Okay. Alright, so this is going to be the expected profit for me, on average, every time this game is played. So let's see what that ends up being. First, what are the types of profit I could make? I could make $5 every time that you got something else. How often do I make $5? 36 out of 52 cards, I will make $5. There are some times that I break even. You gave me $5, I gave you $5 back. That happens with any other heart. How often is that? 12 out of 52. Okay, there are some times that you give me 5, I pay you 10. So I have lost $5. That happens with any other ace. That was 3 out of 52. And then the big winner, negative 95, because you gave me 5, I gave you back 100. That happens 1 out of 52 times on average. So here is this formula. This E of X stands for expected value. That's the same thing as the mean. It's what happens on average in the long run. The law of large numbers. So out of many times playing this, this is what will happen in the long run. Even by the end of the day, if I play this in every class, by the end of the day, I still might be losing. Okay? But in the long run, I would be coming out to something we're going to see here in a minute. All right. Do you know that this symbol means, is a capital sigma, means to do what? Sum. Okay? We are going to be summing the product of this little x with an I. That is your individual x's. That is these amounts. These individual x values. Okay? And you multiply those by their individual probability of happening. that you have already told me. So here's how that works. You can't do this formula. I mean, there's not like you plug numbers in and boom, the calculator gives you the mean and the standard deviation. You have to do this out by hand, and then of course you can use calculator to do the computation. But so my expected profit is $5, and that will happen 36 out of 52 times, plus $0, and that happens 12 out of 52 times, plus negative $5, and that happens 3 out of 52 times, plus negative $95. That happens 1 out of 52 times. That sums to $1.35. So my question is, how is this saying I make $1.35 per play when I can just make 5, 0, negative 5, or negative 95? Good. $1.95 is the average per play. So this average per play is now turning into continuous. Now it could be any amounts. Okay? So this is the average per play is $1.35. Very good. So I'm saying, yeah, come on, let's play, because the more I get playing, the closer I get to that average of $1.35 per win, or per play. All right. So the interpretation of this is that Ms. McClellan will get to buy her son beets. No. Ms. McClellan will profit $1.35 per play. It's not all though. On average, okay, on average is crucial because $1.35 isn't a realistic option in the long run. Law of large numbers happening right there. In the long run, it'll settle down to that. Okay, that's goal number 2. Very good. All right. Next thing, goal number 3. So that was the mean. Now we do the standard deviation. So the first thing that you need to know on your standard deviation is I boo-booed when I wrote your notes here, and I left off this little squared. So you need to put that squared in there right now. Put this squared in there. And what happened was this weekend when I was doing my answer key for this, I kept getting a negative answer. And I was going, what the heck? I can't have a negative standard deviation. So I checked it a few times, and then I realized, oh, okay. Because see, standard deviation is that distance from the mean. That's a positive value. I remembered then that I had forgotten the squaring there, which is making it positive. And by the way, notice, this formula gives me the variance. The variance is the what? Square of the standard deviation. See, because I had to square it. So let's do that. Here we go. The square of the standard deviation is this. Okay, we are going to sum up the, and what am I going to put in parentheses? What is each one of these x with the little I? That's my individual profit, the $5, the 0, the negative 5, the negative 95. Hey, what's this right here? This minus the mean. What's that? Yay! Very good. That's this $1.35. It is critical that you get that mean right, because if you don't, then your standard deviation will be wrong, because you're using it in there. Okay, see? So very, very important. All right. And then you square that quantity so that it is not negative. And then multiply it by the probability. So here we go. All right. My first profit was $5 minus the mean of $1.35. Quantity squared times the probability of that event, which was, what was the probability of me getting $5? 36 out of 52. All right. Plus the next thing. Okay, so the next one, my profit was breaking even, so that was 0. Minus the mean of $1.35. Quantity squared times the probability of that event, which was when you get any other heart, 12 out of 52. Plus, okay, what other type of profit do I make? Negative 5 minus $1.35 quantity squared times the probability of that happening, which is the other aces, 3 out of 52. And there's one more. Plus, I'm going up the edge here. And that was me doing what? Losing 95. So negative 95 minus $1.35 quantity squared times the probability of that happening was 1 out of 52. Okay? So, ta-da! It is very tedious. Let me tell you, let me give you a word of advice. After you type that in your calculator, in your graphing calculator, you have all that written out. I always go back and kind of look back over all my numbers in there before I compute it. That standard deviation squared is $190.05. So if that's the standard deviation squared, then what is the standard deviation? The square root of it. Don't forget to take the square root. That comes out to $13.80. It's actually quite a big number in comparison to the average of $1.35. But anyway, okay, so before we go on, so that's actually goal 3, computing the standard deviation with the formula. Okay? So before we go on, though, to the next goal, I kind of want to give you a little plant a seed as to what the heck we do with these things and what I'm going to give you a small little notes video tomorrow of what this means and what you do with it. And so here it is. I asked you to draw a normal model to represent the expected profits that I will make for this game. So here we go. This is the average profit per play. Okay, so what will the average profit per play be? $1.35. And how many standard deviations up are on the normal model? 3 up, 3 down. Okay, and each one of those standard deviations is actually quite large. It's $13.80. So I've put some numbers in here to kind of give you an idea for the wide range of profit margin. 15, 15, 28.95. Anyway, it could go all the way up to $42.75 positive, or all the way down to $40.05 negative. Now, I'm not exactly sure how that can average out to that big per play. I wonder if this means like per whole person, because if it's max of 5, then it could be more than that. But anyway, that's another question. By the way, this one standard deviation down is negative 12.45. So, do you know what? This line right here, which is only a tenth of a standard deviation away from the mean, is break even. What's break even? My profit of 0. So let me just give you an idea as to why gambling is so appealing. All in this direction, the players are making money off of me. Okay? That's a large amount. This is 46% of the time people are making money off of me. And I'll show you how to compute that tomorrow. We're going to get into that tomorrow. That is what makes gambling so appealing. 46% of the averages of events is profits, and I'm losing money. That's what makes it so appealing. But I know in the long run, I will win out. Okay? So, there you go. It's kind of a little glimpse into the future. Okay. We are getting close. We are to goal number 4. Just 2 goals left. Good. Okay, so here we go. Hey, the good thing about goal number 4, we can pretty much review. We have already done this concept before. It's just adding, subtracting, multiplying, and dividing the mean and the standard deviation. You know what to do that. So look here. Do you remember, this is a number line down here, and if I had normal model, this means if I add, this will shift up. If I add, it didn't separate it. Okay, so if I add, this will shift up, and the mean will get larger. If I subtract, it will get smaller. So is the mean affected by adding and subtracting? Is the mean? Yes. The mean is affected by adding and subtracting. Standard deviation is not. So the mean is. It is also affected by multiplication and division. But the standard deviation is what is not affected. If this is one standard deviation, then shifting up and down does not change the size of the standard deviation. Adding and subtracting doesn't affect standard deviation, but what does? Multiplication and division. Okay? Alright, so there you go. That's all of those ones. Now, let's just go ahead and put that, what happens, the reason that this happens with this concept is it's actually usually changing units. For example, you might go to the average number of repairs, and I want to turn that into cost per year. So I'm going from repairs as a unit to money as a unit. Okay? That's why you do this. That's why you need goal number 4. Here we go. Joe's Pizza and Pasta leased a commercial grade dishwasher for 4 years, and the expected number of repairs on the Samsung washer is 0.45 each year. What in the world? Why is that 0.45? How can you have 0.45 of a repair? Because it's the average, okay? So keep that in mind. The expected number is not necessarily realistic because it's an average. All right. So, standard deviation for that same year is 0.6. Now, the service contract, we're going to transform repairs into money. And that transformation equation is the cost is $110 plus $65 per year, or per repair. Sorry, per repair. And that's for unlimited repairs. So even if it has to be replaced, they show up, and you just are charged $65 for them showing up, and you get a new dishwasher. Find the mean for the cost, the standard deviation for the cost. So here's how you write that. The mean cost for the dishwasher is. Mean is affected by what parts of that equation? Mean is what? Both. The adding part and the multiplication part. Very good. So that is affected by the $110 plus the $65 per repair. What number goes there? 0.45, because that's the average repair amount in a year. That comes out to $139.25. So as a business owner, I am responsible for a budget. Okay, I have to manage my amounts, okay, expenditures. And so this is an approximate that I can expect to spend per year for that dishwasher. Okay? All right, but with what standard deviation? I mean, is it like up $5, down $5, up $50, down up $500? What kind of variation on this number would I expect? How much could it go higher and lower? Okay? So you see why standard deviation in business matters. I need to know how variable is this number. What do I need to account for? All right, so that's the standard deviation for the dishwasher. That is affected by what parts of that transformation? The multiplication. So that is $65 times the what? Not 0.45. was the standard deviation for repairs, and that amount is $39. See, so as a business owner, that's giving me an idea of how far I could be off, you know, within one standard deviation. That gives me an idea of what I need to budget for. All right. That's it. As reviewed for goal number 4. Last goal. All right. Last goal happens when you have more than one variable. For example, the dishwasher you have to account for, and as a business owner at Joe's Pizza, I think it was talking about, you have more than one appliance. So I want to talk about today the dishwasher, that's one variable of events, and we're also going to talk about the oven. So we got service contracts for both the dishwasher and for the oven. And we're going to talk about how much total should I expect on average to pay for the maintenance and repair on my appliances. Okay? And within what standard deviation? That's what's next. So here we go. We are adding and subtracting more than one variable. So, fact number 1. It's nice, it's good. But guess what? The means do what you'd expect them to do. If you are adding the costs of the dishwasher and the oven, boom, you just add their means together. Okay? And that would give you the mean of the total. So that's nice. The means do what you expect them to do. Let's go down to this for example and do that. For example, if the repairs on the dishwasher in a year average $139.25, which that's just what we figured out a minute ago, and the mean for the standard deviation for the dishwasher is $39. Okay, and they have a service contract for an oven, and the mean cost for the oven is $115 with a standard deviation for the oven of 27. Okay, so I am interested in, as a business owner, what is my liability for my combined appliances of those ones. And of course you'd be having more, and you just do the same thing with more. So here's how you notate that. The mean for the dishwasher plus the oven equals. And what did I say that you get to do on that? You just add them like you normally would. And that's going to be the $139.25 plus the $115, and that's $254. Wait, $254.25. Okay, good. All right, so as a business owner, this is what I can budget for, approximately my cost for maintenance on my appliances. Okay? All right. Good. That's fact number 1. Just 2 more facts. Fact number 2 is about standard deviation. How is that handled? Well, guess what? You don't just add the 2 standard deviations together. That would be way too much. Okay? So there's a lot of upper level math that is involved in coming up with the amount of the way that they combine together. But in summary, a quick way to understand that has to do with the Pythagorean theorem of statistics. It's very similar to if you had a triangle and you had an amount of variation here, an amount of variation here, then the combined amount of variation, and this in the real world, you know, with statistics coming from orthogonal vectors and all these other different higher mathematical things, but I can simplify it to you, telling you that your total combined is going to be this amount here, which is like your hypotenuse in Pythagorean theorem. So in this, whereas Pythagorean theorem, a squared plus b squared equals c squared, the c is the square root of a squared plus b squared. If you just solve for c, you're getting the square root of the standard deviations squared. Because you cannot straight up add or subtract standard deviations. You have to go through the Pythagorean theorem of statistics. So, let's do that example. See here? The standard deviation of 2 items added together is the square root of first one's standard deviation squared plus, and this is always plus, never, ever, ever minus the other standard deviation squared. So let's go down there with the dishwasher and the oven and do that. So the standard deviation for the dishwasher and the oven is not $39 plus 27. That would be too big. That would be too much variation. It is going to be then what? The square root of 39 squared plus 27 squared. And that comes out to $47.43. Now, do you see how this is bigger than both of the legs, 39 and 27? This should always be more variation than these variations individually, but not as much as them added together straight up. Because you know what? Hey, if you're not sure how much the dishwasher's going to cost, and if you're not sure how much the oven's going to cost, then you are even more unsure of how much their combined cost is going to be. This is more variation here. Okay? So that's what's happening. And the final idea for today is this, fact number 3. Even if you want to figure out the difference in their standard deviations, the difference you still add. Whether you are combining standard deviations or subtracting your variables, your standard deviation is always larger by you add in the Pythagorean theorem. And I want to show you a real life example of that, demonstrate that with our little cereal box problem on the back. Alright, here we go. You have a box of cereal coming down the assembly line. And so that averages out getting, for the box, $12.04 ounces, or 12.4 ounces, sorry, of cereal. And this, now, is the assembly line always going to put the exact same amount in those things, in those boxes? No. The machinery is going to vary a little bit. When those machines come down, it's going to be a little less, a little more. Well, the variation on a box of Lucky Charms is 0.1 ounce. Okay. Well, guess what? In the morning, you wake up and you pour yourself a bowl from a fresh new box of Lucky Charms. Your average bowl is 1.6 ounces of cereal. Now, that's weight, not volume. And the standard deviation of that bowl, you know, it's a little more variable because sometimes you're hungrier than other times, so you're kind of more varied. It's in the morning. So it actually has a higher variation, 0.2 ounces. All right. So the question is, find the mean and standard deviation for the amount of cereal that is left in the box after you pour your bowl. What mathematical operation is that? Subtraction. We are finding the difference. We are subtracting out the bowl. Okay, so let's do that. So the mean of the box minus the bowl is straight up what you want it to do. Box minus the bowl. 12.4 minus 1.6 leaves 10.8 ounces in the box on average. Okay? With what standard deviation? The standard deviation for box minus bowl is what? The square root of 0.1 squared plus 0.2 squared. That number comes out to be 0.22 ounces. So I had miscalculated something earlier and I thought it was strange because this wasn't big. This has to always be bigger than these individual standard deviations alone. Isn't the hypotenuse always bigger than its legs? Yes. So if you do not get this number bigger than each individual standard deviation, then you did something wrong. Okay? And here, one last thing, it should make sense. Because hey, guess what? if I'm not sure how much cereal is in the box, okay, I'm not quite sure, I'm a little uncertain, then I pour some out. And I'm not sure how much I poured out, so then I'm now even more uncertain with what's left in the box. I wasn't certain, poured some out, wasn't sure how much that was, so I have even more uncertainty with what's left in the box. All right, so in summary, let's kind of mentally go through our five goals. The vocabulary for discrete and continuous. The formula for the expected value. The formula for the standard deviation. Oh wait, what's done here? Formula for the standard deviation. Okay. Changing units. What goes through adding and subtracting, and the standard deviation only affected by multiplication. And then finally, the rules of combining two variables. They add and subtract like normal with the mean, but the standard deviation goes through the Pythagorean theorem of statistics. Now, I want to do some of the problems with you on the homework first, to make sure you are good to go and solid on your homework tonight. So open that up. Plus, I have two small little corrections I have to make because I boo-booed on that also. All right. First correction that needs to happen is on number 1C. I forgot to put that squared in for the formula for your standard deviation. Okay, so if I write that in, or else you're going to get negative standard deviations like I did and go, what the heck? All right. The other correction is number 2C. So go down to number 2C. The question should read, find the expected number of children, not the expected number of boys. Find the expected number of children that the couple will have. Okay, that's all the corrections, but we're going to do this probability model together and a probability model for number 3, just because these are kind of the more difficult things to come up with, is these charts. So we're going to do that together. Here we go. Number 2. A couple plans to have children until they get a girl. But they will not have more than 3 children, even if they are all boys. Okay? So that's the name of the game. So we're going to list all the possible outcomes that couples that play this particular set of rules could have. Options that they could have, so the set of children that they could have would be, how would they have one child? What happens? They have a girl, straight out of the chute. Okay? What else could they have? To have 2 children. How would having 2 children? They would first have a boy, and then they'd try again, and if they got a girl, then they'd stop. All right. How could they have, I'm sorry, what? Oh, that's a comma. Sorry. Oh, a bracket. That's a little scribbly bracket. Okay. Is that better? Okay. Because it's a set. How do they have 3 children? They could have a boy, and then have a boy, and then, yay, it's a girl. But regardless of whether they have a girl or not, they will be stopping with 3 children, so they might end up with 3 boys. So this is the set of possibilities. And if we are assuming that the boys and girls are equally likely, let's find the probability of each. What's the probability that this first thing's going to happen? Straight out of the chute, having a girl. That is 50-50 chance, so that probability is 1/2. All right, what's the probability that the first one's a boy and then the second one's a girl? 1/2 for the first one being a boy, and 1/2 for the second one being a girl. And when you have this and that multiplication, that is 1/4 of a chance to have 2 children. Exactly 2 children. All right, how about this? Boy probability times a boy probability times a girl probability. So that's going to be 1/2 times 1/2 times 1/2, for a total probability of 1/8 is the likelihood of them having a boy, and then a boy, and then a girl. How does that work for boy, boy, boy? Same. 1/2 times 1/2 times 1/2, which is 1/8. So now let's fill in our probability model on part B. Based on our amounts listed in part A, what's the probability of having one child? That's this situation here. That's 1/2. What's the probability of having 2 children and stopping? That's 1/4. What's the probability of having 3 children and stopping? It is 1/4 again because, well, a couple of reasons. First, this plus this plus this have to total up to 100% of the possibilities. Okay, so straight up right there, that's why that's 1/4. It has to be. But look, the reality is this way here plus this probability here, 1/8 plus 1/8 is 2/8, and that's 1/4. So boom, that is in your probability model. And you would then do part C, which is the expected number, and then the standard deviation. But let's do one last probability model together, because this is the one that typically gets most struggled upon. It is the insurance policy one. Okay, so here's what happens. This is like real life. This is a simplistic version, but this is a real life way it works. Okay? So an insurance policy in this case is worth $100. So every client that wants this at the beginning of their policy year pays $100 up front. And then the policyholder, so the insurance company is going to pay them $10,000 if they have a major injury. Okay? And that means going into the hospital. Or the insurance company will pay them $3,000 if they have a minor injury. They didn't go into the hospital, but they did lose work. All right. Now, it says the company estimates, but really the actuarial scientists would have come up with. The actuarial science, this is where the big bucks comes in. Their entire rates are based on this number here. That 1 in every 2,000 is estimated to have a major injury. And 1 in every 500 is estimated to have a minor injury. That is critical to make those approximations accurately, and they collect tons of data to come up with those. So this is a simplified version, but that's critical numbers right there. So here we go. Let's create a probability model for the profit that the insurance company is making. So straight out of the bag, everybody's going to be doing what? Paying $100, and we're going to find that probability shortly. What else could happen? The insurance company could have to do what? Pay for, let's do major injury first. If I pay you for a major injury, I lose $9,900. Why $9,900? You gave me $100. I gave you $10,000. I am out $9,900 as the insurance company is out $9,900. And how often are they out $9,900? 1 out of every 2,000 clients. Okay. All right, and then now you get the way this works. For the minor injury, they would be out how much? $2,900. They give you the company $100. The company pays out $3,000. So the company is out $2,900 for every minor injury, and that happens 1 every 500 times. So how do I find this leftover amount? Okay, go. Good. Take these, total them up, and subtract it from 1. If you go 1 minus these two things, you end up with 0.9975. So 99.75% of the clients will be paying the insurance company and not getting anything back. Now, once you do this and you find the expected profit of the policy, do you think that's a positive number? Yeah, it better be. If that insurance company is going to stay in business, then this final thing here better be positive, or else, then it's not a business. You're doing charity work or whatever. Okay, so that's all I wanted to do on that. So again, in summary, you do your Chapter 16 Part 1 homework. You will get stamped by it for it tomorrow as the video explaining it is happening. And then I will quiz you Friday.